Here is an example for Norton's theorem. Now here we have to find the current passing through the 6 ohm resistance using Norton's theorem. Okay. The circuit consists of 5 ohm resistance, 10 ohm resistance and 6 ohm resistance. In order to solve the problem, I have redrawn the circuit once again. Okay. In the question, it is required to find the current passing through this 6 ohm resistance. So I'm going to mark 2 points, A and B, and in the first step, how to remove the 6 ohm resistance, or I have to disconnect the 6 ohm resistance from the circuit. Okay, this is our first step in which I have disconnected the resistance 6 ohm from the basic circuit given. Okay, then the new circuit will be like this. Okay, so next let us pass through step 2. In the next step, we are going to find the Norton's current. For what purpose? We have to draw, or we have to find the Norton's equivalent circuit for this circuit. Okay, we have to replace this circuit using corresponding Norton's equivalent circuit. So we need two components. So first one is Norton's current and another one is Norton's equivalent resistance. Okay, right. So let us find the Norton's current source first. For that purpose, we have to short circuit the current. Why we are going to short circuit? Because we know that we know that the Norton's current is the short circuit current between the points A and B. So that we are going to short circuit this. Then the new circuit will be 20 voltage source, resistance, 10 ohm resistance, then A and B, then short circuit. Okay, this is a 5 ohm resistance and this one is 10 ohm resistance, and the current flowing through this short circuit, that is known as Norton's current IN. If we short circuit A and B, the current which is flowing through these 2 points A and B is known as Norton's current. So now let us find the magnitude of the current IN. If we analyze the circuit carefully, a current that will flow from the 20 volt voltage source through 5 ohm resistance reaches the first node here, and there should have a tendency for that current to pass through A and B, and also the current have the same tendency to flow through this 10 ohm resistance also. Means the current upon reaching this point can flow through this area, or else it can flow through the 10 ohm resistance also. But here we have to apply the logic that current will always flow through null resistance path, if any. Okay, if there is any null resistance path, null resistance in the sense, for a short circuit means resistance is equal to 0. Resistance is equal to 0 means null resistance. If there is any null resistance or path with 0 resistance exists, the entire current will flow through that region. Okay, means upon reaching the current at node 1, it will have a tendency to flow. A portion can flow through this region or through this region, but the entire current flow through A and B. There will not be any current flow through the 10 ohm resistance. Why? Because as I said earlier, in the short circuit path, the resistance is equal to 0. So current will always flow through a null resistance path. Therefore, the entire current flow through the short circuit path only. There will not be any current through the resistance. So let us draw the corresponding circuit once again. 20 volt, then followed by 5 ohm resistance, then this node, then A short circuit, corresponding current IN, then corresponding another node B, and there will not be any current flow. Current will flow through this area. Okay, means there is no 10 ohm resistance in this circuit. Means the 10 ohm resistance in this circuit is meaningless. There will not be any voltage drop here. Why? Here there will not be any voltage. Why? V is equal to 0 here. Why? Here V is equal to potential difference, equal to I into R. What about the current flowing through this path? That is equal to 0 into resistance is equal to 10 ohm itself. Anyway, 0 into 10 gives 0 volt. Means here the drop is equal to 0 volt. Okay, as there is no current flowing through it. Now I have to find what is IN. All of you know that I is equal to simply the potential difference by resistance. In this path, what about the current IN? Applying this formula, we can write IN is equal to potential difference. What about the potential difference in this circuit? That is 20 ohm. Okay, sorry, 20 volt divided by what about the resistance in this path? Only 5 ohm resistance. So the current we are getting is 20 by 5 is equal to 4 ampere. That is the Norton's current IN. Okay, let us mark it as equation number 1. Now let us move to the step 3. Here we have to find the Norton's equivalent resistance Rn. Means we have to find the Norton's equivalent resistance across RAB. RAB. How many resistance are here? Here we have two resistance, 5 ohm and 10 ohm, and one more voltage source is there. Then with the presence of 20 volt voltage source, how can we find the equivalent voltage source across A and B? As we know, if there is any voltage source or a current source, while calculating the equivalent resistance, we have to nullify that. If it is a current source, we have to make the current source equal to 0. How can we make the current source equal to 0? Simply by open circuiting. All of you know that in an open circuit there will not be any current flow. Okay, right? Here we have only a voltage source is there, 20 volt voltage source is there. While calculating the equivalent resistance across A and B, somehow we have to nullify this 20 volt voltage source. How can we nullify a voltage source? By short circuiting. By short circuiting this voltage source, we can make it 0. Short circuit in the sense we found that the voltage itself is equal to 0. So let us redraw the circuit after short circuiting the 20 volt voltage source. Okay, right? Okay, here I have nullified the effect of 20 volt voltage source here by simply short circuiting. Okay, by means of a wire. Okay, I removed it or nullified it. Then the remaining 5 ohm resistance and 10 ohm resistance here, 5 and 10. Okay, across the point A and B, we are going to find the resistance RAB. That will be the Norton's equivalent resistance. What is RAB, or what is the relationship between 5 ohm and 10 ohm? If we look at this network, we can say that this 5 ohm and 10 ohm are parallel to each other. 5 ohm resistance is connected in parallel with 10 ohm resistance. Therefore, Rn will be equal to 5 ohm resistance in parallel with the 10 ohm resistance. That is by using that formula R1 R equivalent is equal to R1 R2 divided by R1 plus R2. This is a formula for a parallel circuit resistance R1 and R2. Okay, suppose R1 and R2 are connected in parallel, then the equivalent resistance will be R equivalent is equal to R1 R2 by R1 plus R2. If we apply the same formula here, we will get 5 into, in place of R1 we have to use 5, and in place of R2 we have to use 10. Okay, 5 into 10 divided by 5 plus 10, that will be equal to 3.33 ampere. Okay, oh, sorry, 3.33 ohms. Now we got the the Norton's equivalent resistance Rn is equal to 3.33 ohm. Let us mark it as equation number 2. Now we have to draw the Norton's equivalent circuit for this circuit. Okay, simply replace this circuit using Norton's current followed by a resistance that should be connected in parallel with the network. Okay, right? Across A and B, we are going to replace this entire circuit using Thevenin equivalent resistance. Thevenin equivalent resistance should consist of a single current source I Norton and a single resistance in parallel with the current source. Now we got the Norton's equivalent current I N is equal to 4 ampere, and just now we have obtained Rn is equal to, or Norton's current is equal to this one. Now let us draw the Norton's equivalent circuit. Norton's equivalent circuit is the consisting of a single current source I Norton followed by a Norton resistance Rn, then point A and B. Okay, what about the magnitude of In? That is obtained in equation number 1 as 4 ampere. That is 4 ampere. Then what about Rn? That is 3.33 ohms. Now, in order to find the current flowing through this 6 ohm resistance, we have to reconnect it back to these points A and B. Now that is our next step. Now connect the 6 ohm resistance back to the circuit, I mean across this point A and B. Now what we are getting is a 4 ampere current source, then corresponding Norton's resistance 3.3 ohm, and here across A and B I have to put the resistance 6 ohm resistance, which is replaced in step 1, right? In step 1 we replaced, we removed the resistance 6 ohm. Okay, right? In the step 1 we disconnected it or removed it from the circuit. Now we connected it back to the Norton's equivalent circuit. Now let us find the current flowing through this one. How can we find the current through this network or current flowing through the 6 ohm resistance? Let us denote it as I6 ohm. That is what we are going to find out. Okay, right. We have to find the current passing through 6 ohm resistance. Now let us evaluate the 6 ohm resistance. By current division rule, we know that, let us refresh the current division rule. Suppose we have a total current I T. T stands for total. That is reached at the point, then a portion of the current is flowing through R1 resistance and another portion is flowing through R2. Now we have to find the individual currents I1 and I2 using current division rule. Okay, by current division rule, I1 is equal to total current into opposite resistance. So what about the opposite resistance? The current just opposite to R1, that is R2 divided by total resistance R1 by R2, and for I2 that will be of course equal to total current I18 into I2. For I2, the opposite resistance is R1. So here we have to write R1 divided by total resistance itself, R1 divided by R1 plus R2. Okay, this is the basic formula for current division rule. Now let us apply the current division rule here also. Here this is for for ampere current, known as Norton's current, reaches this point and it is split into or divided into two currents, I 3.33 ohm and I 6 ohm. We have to find the current flowing through the 6 ohm resistance. So I 6 ohm resistance by current division rule, that is equivalent to I2 in this figure. Okay, what about the total current? This is the total current. In our case, that is Norton's current, that is equal to 4 into, okay, R1 divided by R1 plus R2. In place of R1, here we have 3.33 ohm divided by total resistance in this loop, that is 3.33 plus 6. Okay, right, that will be the current flowing through 6 ohm resistance. The magnitude of this one is equal to 1.43 ampere. Okay, that is our required solution. Thank you.